Previously on
Clever Cracker Square.
physics, we learnt that, well, we mentioned that Boyle's law is a bit silly.
It is. It says that pressure is inversely proportional to volume, where the temperature is constant.
Except the temperature's never constant. That doesn't have anything about pumping your tyre, temperature increases on the wires, any things.
When you increase the pressure, the temperature increases. And Boyle's law says that this is true as long as you ignore the thing that always happens every time ever.
Now that's quite silly, isn't it, Wayne?
It is very silly. How many other laws do that?
Well, Ohm's, Hooke's, Henry's, Fick's. There's quite a few that do it, actually.
You're right. Quite a lot do that. But we're gonna move on from that silly law.
So we're going to improve it. His law was created based on ideal gases, and they would follow his law.
Yeah, as you increase the pressure on an ideal gas, the temperature doesn't increase. And so they follow another special law for pressure.
Yeah.
Equals a third rho average speed thing E squared.
And that's very nice, but that doesn't help us at the moment.
It doesn't help us, because what about every other gas ever that actually exists?
And so we have to find something for them. Which we have. Not personally, but there's a thing.
There is. And that's, I'm going to write it a bit bigger.
Yeah.
P1
Our P1 times our V1 over our T1 is equal to our P2 times our V2 over our T2.
And then it's just plonking numbers into a formula, really.
It is. So let's do that.
And I'll get a word example up.
Yeah. It's not too complicated. The only thing you need to remember, which is really important, is that your temperature is always in Kelvin. So you need to convert that. You're not trying to convert that. We'll show you in a second.
Yeah. So, this question.
Yeah.
A one cylinder of a diesel engine
I love
in one cylinder of a diesel engine.
Okay.
Talk us on.
I'm in the place.
You're in the place.
Yeah.
Is it nice? What car is it?
Well, I don't know. I'm just inside the cylinder. Really, it's a bit cramped.
You're about to get squashed.
Oh no.
A piston compresses air at a temperature of 23 degrees Celsius.
That's fine. That's room temperature. That's right.
Yeah, it's okay for now. There's a pressure of 1 times 10. I'll lay it right actually.
All right.
So the pressure is 1 times 10 to the 5 pascals. And it's.
Oh, right. Yeah, okay.
Okay. And it does this to 1/25th of its original volume. So.
Right.
You know, that's pretty important.
V1 will equal 25, say, and our V2 will equal 1.
Yeah, you can think about
Essentially that.
Yeah.
Our V2 will equal our V1 over 25.
I think that's a better way.
Yeah.
So it does that, and the pressure rises.
Alright.
So this is where the trick dies. 9.06 times 10 to the 6 pascals. Also, you know, you're in a car, so you'd have to be quite small to start with.
I'd have to shrink a lot, wouldn't I? Yeah.
And you'd be given out this nasty fumes that no one likes.
I don't like diesel engines. They're not my friends.
So what with the temperature after this compression is what it's saying?
So we want to find our T2.
So let's plug some numbers into a formula, shall we?
Let's first.
Probably this one.
Probably that one's a good idea. Other formulas less helpful.
Yeah.
So first, I have to convert this into Kelvin.
Yep. So you just add 273.
Yeah.
Which is 296.
Yes, it is.
So
that's our temperature.
We've got 1 times 10 to the 5.
Yeah.
P1 times V1. We're just going to call it V1 because we have no proof that it's 25.
No, yeah, that's just a ratio there.
It's just a ratio. So it's just V1 at the second divided by T1,
T1,
as Triv said.
It's in Kelvin, so it has to be 296. And it's not degrees, it's just like that.
Yep. And that
then
equals P2.
P2, we have that. 9.06 times 10 to the 6 times, and it's going to be times 2 our V2. And our V2 is V1 over 25.
So we can say that that's times by V1, and there's going to be a 25 on the bottom.
But there's also our T2 at the bottom, so 25 times our T2.
I'll just call it T because T1 is already in and we're just trying to find out T.
That's reasonable. And then you're just simply rearranging to find T.
Yep.
So you should be able to notice, if you haven't noticed already, our V1s on each side will cancel. Which is quite handy because when I first saw this sort of question in physics, I saw an unknown there, and I saw an unknown there, and I saw 3 unknowns, didn't know how to deal with it.
Don't have to deal with it, but the way they get around that is by asking a ratio. So be prepared for something like that.
Yeah.
They may well just give you the volumes. And then you just rearrange, the V's are now gone.
Yeah.
You're going to get...
T is equal to 9.06 times 10 to the 6 times 296 over 25 times 1 times 10 to the 5.
296 over 1 times 10 to the 5 times 25. We'll give you a number.
We give you an AT, which will be in Kelvin.
Yep, and it's 1070 Kelvin. There's no degrees Kelvin, it's just Kelvin.
So if they ask for the answer in degrees Celsius, you just take away 273 from that.
Yep, if they don't, then they just give you somewhere to answer.
I'd
Either
do
would
it
be
in
good,
Kelvin.
and you'd give what you're measuring it.
Yeah.
So if you're measuring in Kelvin, just put a K. If you're measuring degrees Celsius, put degrees Celsius.
Mm-hmm.
But it initially gave you in degrees Celsius. If it doesn't give you anything, just to be nice, I'd give it back to them in degrees Celsius, because they gave it to us in degrees Celsius.
Yeah.
So you minus 273 if you're going the other way around,
Yeah.
and that gives you, I could have just minused it really, but 797 degrees Celsius.
Which is quite toasty.
Yep, we do
Don't keep
not
going.
want to be in a piston at that
No.
point. And there you go, that's that in a
There you go.
nutshell.
Yeah. So I think I'm done. I'm done boiling. My kettle's ready.
Ah, tea.